Welcome to my fourth video connected to star and delta connection problems. Here we are going to solving multiple number of star problems and also the delta problems. To solve this star and delta problem, so we need the two equations. One is current equation and voltage equation connected to star, and current and voltage equation connected to delta. So once we go through the proper analysis, so these things are very easy. So now we are going to discussing star and delta problems. Now very first problem is this. It's a balanced three-phase star connected load. So given 400 volts, 50 hertz, current in each phase is 30 amps and lags 30 degree behind the phase voltage. So here you need to calculate total power, phase voltage, draw its vector diagram. So as per the previous discussion, first we will go through the equations for the star connection. That's why IL is equal to I phase. But as per the problem, so here the 30 degree given the phase current. So phase current and line current both are same. That's why so line current and phase current is equal to 30 amps. And also given 400 volts, that is called VL. VL is equal to 400 volts. And as per the equation connected to the star, VL is equal to root 3 into V phase, or V phase is equal to VL by root 3. So once VL value 400 by root 3, answer is 231 volts. So this is the star connected network. As usually, the line voltage is 400 volts is given. Line voltage that indicates so R to Y or Y to B or so R to B. So whatever EL indicates 400 volts, and here also 400, remaining also 400. And also here the 30 volts, that is the phase current. Phase current, here we are indicating the 30 volts is entering. That's why I phase. IL is equal to I phase in the case of star connection. And also here also 30 amps phase current, and here also 30 amps phase current. So very first, so we need to calculate the total power. So as usually total power in the case of star connection, P is equal to root 3 VLIL cos phi. Or so we can use this equation also, P is equal to 3 into V phase I phase cos phi. So once we will substitute, so root 3 as it is, VL is 400 volts, IL is 30, cos phi is the cos 30. So total answer is 18,000 watts, or it is also called 18 kilowatts. So the second point is we need to calculate the phase voltage. Phase voltage V phase, that is VL by root 3, answer is 231 volts. So that 231 volts, so we will show here. So in this phase is called phase voltage. Here also same and here also same. But the third factor is, so need to draw the vector diagram. So in the case of vector diagram, here, so you can take the ER 231 volts as the reference, then EY also same, then EB also same. We already know that. So this is 120 and this is 120 and remaining is the 120 phase displacement. So according to the problem, current in each phase. So this is the phase. This current along with this current along with this current. Current in each phase is 30 amps and lags 30 degree behind the phase voltage. Suppose this is the phase voltage. So for this phase voltage, I mean the current, this is the IR lagging at an angle of 30 degree from this phase voltage. And this is the phase voltage EY, and so IY is this. This is the IY lags at an angle of 30 degree. Then followed by this is the phase voltage. So current is IB. IB lagging at an angle of 30 degree. So this is the vector diagram. But so we need to show a proper line voltage. For example, this is the line voltage. So this is the 400 volts is given in the problem. That line voltage also we need to mention in the vector diagram. So line voltage, so as usually in the derivation of the star connection, that is ERY is equal to vectorically ER minus of EY. As usually here, ER is already here, so EY is here. So you need to proceed this minus of EY like this. See, minus of EY. So you need to extend this according to the law of parallelogram principle. So like this, then this. So the resultant is the ERY. So as usually, so we already known the angles connected to this vector diagram. So this is the vector diagram connected to this problem. So first he is asking the power, second thing he is asking the phase voltage, third thing he is asking to draw the vector diagram. So come to the second problem. Second problem shows three equal impedances each having a resistance of 8 ohms and inductive reactance of 6 ohms connected. First one is the star, second one is the delta. So across three phase 440 volts system. So first we need to calculate the phase current, second one is the line current, third one is the total power consumed. See, whatever the problem, either that is belong to the star or belong to the delta. First star means, so we need to write the equation. IL is equal to I phase, VL is equal to root 3 into V phase, V phase is equal to VL by root 3. So VL value is 440 volts divided by root 3. Answer is 254 volts. So as per the impedances given in one phase, so 8 ohm resistance and 6 ohm, so inductive reactance. And here once again 8 ohms and 6 ohms, once again here 8 ohms and 6 ohms. So this is the line voltage, that is 440 volts. We will call that is EL or ERY also. So here also 440 volts, remaining also 440 volts. So this is the one impedance connected to one phase. That's why that impedance, how to calculate impedance means, impedance that is Z is equal to root of R square plus XL square. That is 8 square plus 6 square, answer is 10 ohms. So as per the problem, we need to calculate the phase current. Phase current means this, I phase. Or this is also called IL. Both are same in the case of star connection. So as we know, according to the Ohm's law, I is equal to V by R. In this circuit, because of the impedance, the AC, so I is equal to V by Z. We will convert this I as I phase. I phase is equal to this V becomes V phase divided by Z phase. Okay, V phase, that is 254 volts, we already calculated. Z phase is, here we calculated 10 ohms. 254 divided by 10, answer is 25.4 amps. Okay, that's why, so once we got the answer of 25.4 amps, IL is equal to I phase, that's why both are same 25.4 amps. And also, we need to calculate the total power. Total power of, so that is, equation is, we already know, root 3 VL cos phi. In place of root 3 is as it is, the VL is 440, IL value just now we calculated 25.4, cos phi is 0.8. Cos phi, R by Z, R value is 8, Z value is 10, answer is 0.8, that's why we substitute that 0.8 here. So total power P is equal to 15.48 kilowatt. So as we know, this is the delta connected. As usually the impedances are connected like this. Finishing end of one coil is connected to starting end of another coil. Finishing end of one coil is connected to starting end of another coil. So as usually the resistance value is 8 ohms, the inductive reactance value is 6 ohms in each phase. This is the first phase, the second phase, and this is the third phase. As usually given in the problem, the line voltage is 440 volts, again here 440 volts, and third also 440 volts. So we know the delta relations. Delta relations actually the line voltage and phase voltage remain same. You can check this phase voltage, that is also same. You can check this line voltage, that is also same as usually given. VL is equal to V phase 440 volts. But equation becomes differ in the case of current values. So to calculate the phase current, so first we need to analyze. So just I is equal to V by R. Also, I phase is equal to V phase divided by Z phase. In place of R, here impedance is Z. That's why V phase divided by Z phase. So V phase we already known that. So that is VL is equal to V phase 440. Z phase answer is 10 already we calculated. The answer I phase value is 44 amps. Once we calculate this I phase value, substitute in IL. IL is equal to root 3 into I phase, root 3 into 44, answer is 76.2 amps, answer is IL. Okay, then at the end we need to calculate the power. As usually power P is equal to root 3 EL cos phi. So root 3 multiplied by 440 multiplied by 76.2 into 0.8. The final answer of power in the case of delta connection is 46.457 kilowatts. So third problem is a balanced star connected load 8 plus J6 ohms per phase is connected to 3-phase 230 volt supply. Find the line current, power factor, power reactive volt amperes, total volt amperes. Here the formula is given in terms of 8 plus J6. Okay, here, so 8 plus J6, 8 indicates the resistive part, I mean the real part. Come to the J6, so there is the imaginary part, that is also called inductive part. That is converted into the impedance. Once again, impedance is equal to, that is the root of 8 square plus 6 square is equal to 10 ohms. So according to 8 plus J6 ohms, 8 is the resistive part and here this is the inductive part. This is total impedance. Then followed by here also 8 and 6. Here also 8 and 6. We can write this reverse manner also, no problem. So both are same. So here R to Y. So given in the problem 230 volts, that is also called EL, also is equal to ERY. 230 volts is here and once again 230 volts. Remaining third line also 230 volts. First we need to calculate the line current. According to the star, IL is equal to I phase. Or to calculate the I phase first. So just like I is equal to V by R. Or in place of R, so we will write the Z. I phase is equal to V phase divided by Z phase. So V phase we already calculated, that answer is 132.79. Z phase is the 10 divided by 10, answer is 13.279 amps. That is also called I phase. As per the star connection, IL is equal to I phase. So second point, power factor. We need to calculate the power factor. Cos phi is equal to R by Z. So R value the 8 as usually. Z we already calculated the 10. So answer is 0.8. Come to the power. Total power. So P is equal to root 3 VLIL cos phi. Root 3 in place of VL 230 volts. Here, so this is line to line is 230 volts. In several problems, in some problem given 230, in some problems given 440. Totally this is RMS value actually. 230 volts line voltage, 230 or 440, this is the RMS value. Okay, this 230 volts, here you will substitute. So IL value is 13.279, cos phi just now calculated 0.8. So power answer is 4232 watts. So value of V phase, that is VL by root 3, 230 by root 3, that answer is actually 132.79 volts. So as per the fourth part, so we need to calculate reactive volt amperes. Actually the active volt amperes, as usually we already know, 3 into V phase I phase cos phi or root 3 VLIL cos phi, both are same. But the reactive part, as per the problem, but reactive volt amperes, that is equal to 3 into V phase I phase sin phi. Here cos phi, here is the sin phi. So reactive volt amperes 3 into V phase I phase sin phi. That's why 3 as it is. V phase 132.79, I phase is 13.279, sin phi is the 0.6. That is answer is actually we need to write in terms of var. 317 var. The long form of var is reactive volt amperes. So fifth one is the total volt amps. The relation of total volt amps, that is equal to total power in watts divided by cos phi. Just like the same equation once again. Actually, here total power in watts we already calculated 4232. Cos phi is 0.8. Answer is 5290 amps is the answer of this problem. Let us move to the fourth problem. This is a balanced 3-phase star connected load. Power is given 150 kilowatts. That power can take a leading current of 100 amps with a line voltage as usually EL 1100 volts, frequency 50 hertz. Find the circuit constants of the load per phase. In phase, per phase, some circuit constants are there, I mean the parameters. Circuit constants. Constants means R, C, L like that. Here, so given EL is equal to 1100 volts, frequency 50 hertz and power is given, that is 150 kilowatts power. Here IL is equal to 100 amps, I mean the condition is given leading. Connected to leading case, 100% is the RC circuit. We need to calculate the circuit constants as R and followed by C. So this is the circuit we written. Here in each phase, resistance along with a capacitance. That's why Z phase. This is one phase. Then come to one more phase, R and C again. And here R and C again. So this is one phase, I mean Z phase, and here also Z phase. So line current, so totally there is given 1100 volts here also and 110 volts remaining also. And here is given in phase current is 100 amps, leading current. 100 amps here also and 100 amps here also and 100 amps here also. So as usually according to the star connection, IL is equal to I phase, both are same, that is 100 amps. Or EL is equal to root 3 into E phase. We need to calculate E phase, EL by root 3. The value of EL is 1100 divided by root 3. Answer is 635.085 volts. That is E phase volts. Here, first the circuit constants. You can calculate R and you can calculate C. First of all, we need to calculate resistance R. So with the help of a relation using the 3-phase power, P is equal to just like a I squared R. As usually power relation. Here 3 phase, that is P is equal to 3 into I squared R. Here P is equal to 3 into I phase square into R. So power is given, that is 150 kilowatts into 1000. 3 is as it is, I phase square is 100 square multiplied by R. R is the unknown value. That's why R is equal to, so this numerator 150 into 1000, denominator 3 into 100 square. Answer is 5 ohm resistance per phase. So we need to calculate the C with the help of impedance way. Impedance way, we already know that is Z is equal to root of R square plus XC square, or Z square is equal to R square plus XC square. We already know XC is called capacitive reactance. Here XC is here, XC is equal to root of Z square minus of R square. We want the value of Z. What way we need to calculate Z? So we already know I is equal to V by R, or R is equal to V by I. In place of R, substitute is Z. Z is equal to V by I. Z becomes Z phase, V becomes E phase, I becomes I phase. So E phase value 635.085. Just now we calculated. The E phase value is 100. That answer is 6.35 ohms is the Z. So this Z you can substitute here. So Z 6.35 square. R value we already known that is minus of 5 square. Answer is 3.9144. So we already know the value of XC, I mean the equation XC is equal to 1 by 2 pi FC, or C is 1 by 2 pi F into XC. So just substitute. C is equal to 1 by 2 pi F. So multiplied by 3.9144. So that answer is 813.175 into 10 raised to minus 6 farads. Final answer is 831.175 microfarads. So from this R value is 5 ohms and this C value is 831.175 microfarads. Problem connected to the star connection. Fifth problem. 350 ohm resistors are connected in star across, so line voltage 400 volts, 3-phase supply. Here you need to calculate, find phase current, line current and power drawn from this supply. And also the second point is asking what would be the above values, same values, if one of the resistors were disconnected. Suppose one resistor is disconnected, what is the phase current, what is the line current and what is the power drawn from the supply. Okay. So as per the problem, so this is the R value in one phase 50 ohms, here 50 ohms and here 50 ohms. So given the line to line 400 volts, the Y phase and remaining is the B phase. So first of all, we need to calculate I is equal to V by R, or I phase is equal to V phase divided by R phase. Here R, only one R is there. That's why R phase that is equal to V phase. The value of a V phase this way, VL is equal to root 3 into V phase, or V phase is equal to VL by root 3. VL is 400 by root 3, so 230.94 volts. That 230.94 volts divided by 50 R phase, the answer of I phase is 4.6188 amps. Okay, so IL is equal to I phase, both are same, that's why 4.6188 amps. And we need to calculate the power as per the problem. P is equal to root 3 VLIL cos phi. So root 3 into 400 multiplied by 4.61. So divided by 4.61. The total answer of power is 3200 watts. So here value is 1. Cos phi is 1 because it's a pure resistive. That's why cos phi is equal to 1. That's why the power answer is 3200 watts. So in the second case, what would be the above values if one of the resistors were disconnected? Here one resistor is disconnected, so remaining two as it is, 50 ohms and 50 ohms. So R phase was not there, so Y phase and B phase. Here we written, so Y to B, that is the line voltage is 400 volts, IL is flowing, so here R and here just like a series circuit, that's it. So IL is equal to V by R. So V is 400 volts. R, we will add both series. 50 plus 50. So 400 divided by 100. So answer is 4 amps, or that is also called I phase. So here only two resistors, and this is only one series circuit. That's why we need to calculate the power, that is I squared R1. I mean I phase square R1. And I phase square R2. The answer is I phase 4 square into 50. Again 4 square into 50. Answer is 1600 watts. Okay. So we will calculate, the line current. So also the phase current. Finally the power. Power is this. Now we will consider the delta problems. So first problem, as usual, a balanced delta connected load of 8 plus J6 ohms per phase is supplied from a 3-phase 440 volt source. Find the line current, power factor, power per phase, and also total power. So this is the delta connected network. So as usually the impedance is given Z phase, that is 8 plus J6 ohms. So this is the 8 and this J6 ohms, I mean this is the inductive part. So this is the one phase, one more phase, and one more phase, the delta network. 440 volts is the line voltage. Here also 440 volts. And as usually in the case of delta, line voltage is equal to phase voltage. Answer is 440 volts. And also we need to calculate the line current. Line current is equal to root 3 into phase current. How to calculate this phase current? Phase current, so we already know, as usually I is equal to V by R, or I phase is equal to V becomes E phase divided by R becomes Z phase. So Z phase we already know that Z phase is equal to 8 plus J6 ohms, or Z phase is the root of 8 square plus 6 square. Answer is 10 ohms. So that 10 ohms we will substitute here. 440 divided by 10, answer is 44 amps. Okay, this 44 amps, that is the I phase. This I phase we will substitute here. IL is equal to root 3 into I phase. Root 3 multiplied by 44. Answer is 76.21 amps. The IL value. So second one is the power factor. That is, as usually, cos phi is equal to R by Z. R value is 8. Z phase is 10.8. Come to power per phase. So for one phase, per phase means one phase. P is equal to E phase, I phase, cos phi. So E phase is 440, I phase is 44, cos phi is 0.8. Answer is 15.488 watts. And fourth one, we need to calculate total power. Total power means 3 into power per phase. Here already we calculated power per phase. Just multiplied by 3 into 15.488. Answer is 46.464 kilowatts. Or so we'll use as usual power relation also. P is equal to root 3 VLIL cos phi. Root 3 into VL is 440, IL is 76.21, cos phi as usually 0.8. Answer remains same. That is 46.464 kilowatt. Second problem, a 220 volts 3-phase voltage applied to balanced delta connected load of per phase impedance of 15 plus J20 ohms. Find out the line current, phase current, power per phase, total real power, and finally what is the reactive power. So this is the delta connection. Here the impedance is given 15 ohms and 20 ohms in one phase. So one more phase and one more phase. So line voltage is given here 220 volts, here also 220 volts, remaining also 220 volts. So first one, we need to calculate the line current. Line current relation in the case of delta, IL is equal to root 3 into I phase. So root 3 into I phase, we need to calculate I phase. So I is equal to V by R, or I phase is equal to E phase divided by Z phase. Okay, so what is the E phase? Actually this is the delta. So delta means, so here this voltage is same and this voltage is same. That's why EL is equal to E phase. So that is 220 volts already given. Okay, so what is the Z phase? Z phase is equal to root of 15 square plus 26 square. Answer is 25 ohms. This 25 ohms will substitute here. And also, so E phase. So value of E phase, that is 220 divided by 25. Answer is 8.8 amps. This 8.8 amps, that is the I phase. This I phase will substitute here. So root 3 into 8.8 amps. Answer is 15.25 amps. That is called line current. Then come to the second, power factor. As usually power factor, cos phi is equal to R divided by Z phase. R value is 15, Z phase as usually 25. Answer is 0.6. Next, third concept. So power per phase, we already know the relation P is equal to E phase, I phase, cos phi. So E phase is 220, that is multiplied by I phase is 8.8, multiplied by cos phi is the 0.6. Answer is 1161.6 watts, or that is also called 1.1616 kilowatts. So last fifth one, total reactive power. So reactive power relation P is equal to root 3 VLIL sin phi, or 3 into V phase I phase sin phi. We already know that cos phi. Cos phi is equal to 0.6, phi is equal to cos inverse of 0.6, 53.13. So sin of that, sin phi is equal to 0.8. So that 0.8 will substitute here, root 3 VLIL sin phi. In place of sin phi, we will substitute the 0.8. So that answer is 464, we will write in terms of a var. So var is volt ampere reactive. Now third problem connected to delta. 3-phase delta connected load consumes a power of 100 kilowatts. Here power is given. Taking a lagging current. Here lagging current of 200 amps at a line voltage of 400 volts. That is EL or ERY. 400 volts at 50 hertz. Find the parameters of each phase. Maybe R, maybe L, maybe C. Find the parameters of each phase. What would be the power consumed if the load were connected in star? Suppose what would be the power consumed load connected in star? This is actually the delta problem. Star also included. We will see what happens. So this is the network. So here two parameters R, and here we need to calculate XL to L. Here also R, and here XL to L. And here also R, we need to calculate XL to L. So in the case of delta connection, so voltage remains same. VL is equal to V phase, IL is equal to root 3 into I phase, or I phase is equal to IL divided by root 3. See, whatever the problem, either connected to the star or connected to the delta, first you need to write this equation, which relation is related to our problem, and that way we will solve the problem, then every problem is correct. And also here power is given, power is equal to 100 kilowatt, and also in the problem itself it is mentioned lagging current of 200 amps, that means that is called IL. Lagging current of 200 amps, that means IL. So we need to calculate R first. So as usually power is given 100 kilowatts. So line current is given 200 amps. So phase current is 200 divided by root 3. So that answer is 115.5 amps. So as usually power 100 kilowatts is given. So we will use the power relation. That is P is equal to root 3 VLIL cos phi. So power relation 100 kilowatts, that is 100 kilowatts. Okay. Or from this equation, so this is the kilowatts. From this equation, cos phi is equal to, this is 100 kilowatts divided by, so root 3 VLIL. Or 100 kilowatts divided by root 3, VL answer is 400, IL answer is, that IL answer 200, 200 as it is. That's the value of a cos phi 0.72. So but cos phi is equal to R by Z, or R phase divided by Z phase, or R phase, or R is equal to Z phase cos phi. The value of a Z phase. So we already know from the earlier equations also, Z phase is equal to E phase divided by I phase. So E phase is 400, I phase is 115.5, answer is 3.46 ohms. This Z phase of 3.46 ohms will substitute here. 3.46 into cos phi is 0.72, so the value of R 2.49 ohms. Then, so we will use the impedance Z is equal to root of R square plus XL square, or XL square, that is equal to root of Z phase square minus of R square. So in place of Z phase square, you can substitute 3.46 square minus of R square 2.49 square. So that answer is 2.40 ohms. So as usually known that, so the inductive reactance XL is equal to 1 by 2 pi F into L, or L is equal to 1 by 2 pi F into XL. So you substitute the known values, 1 divided by 2 pi into 50, XL value is 2.4. So final answer of that L value is 19.09 H. So this is the answer connected to, the first part. So second part, suppose if the load connected in star. So we will go for once again the star connection. Here equations are different. IL is equal to I phase, EL is equal to root 3 into E phase is equal to EL by root 3. So EL, so value of EL 400 by root 3. So that answer 231 volts. That is called phase voltage. Whatever two voltages, that is phase voltage. And here I phase is equal to E phase by Z phase. So E phase we already know that 231. So Z phase is 3.46. We already know. So that answer is 66.76 amps. That is also called IL, or also called I phase. So at the end, we need to calculate the power. Power P is equal to root 3 ELIL cos phi. So once you can substitute EL value is 400, now IL value will be changed here. So because it is a star connection. IL, so 66.72. So cos phi is 0.72. Cos phi power factor remains same. So either you can take the star or you can take the delta. Power factor remains same. That's why the power, answer of power 33301 watts, or that is called 33.3 kilowatts. So these are the problems connected to star connection and delta connection. So from the beginning concept, so here only thing to calculate either phase current or line current, then followed by the power, and also so whatever the circuit constants, either R or L and C. I hope you understood this in a better manner. So please share, please like the video, and also subscribe the video.